Without a doubt, Freeflight is a pure form of model airplane flight. With radio control and control line models, the pilot has the ability to adjust the model to meet the unpredictable whims of the wind, as well as to compensate for bad flight characteristics that might be inherent in the model. But Freeflight is different. Once the model is released, it's on its own, and is indeed flying free. Perhaps the most interesting types of Freeflight models are those powered by rubber. A far cry from the mistaken concept of winding up a rubber band. These models range from easily constructed types such as the thermal dart to the highly sophisticated Wakefield designs flown in international competition. For pure grace and flight, there are the indoor models. Their dreamlike flight is the result of hours spent building and testing until just the right combination of rubber motor and airframe has been found. The idea is to have the model climb as high as possible without getting caught in the rafters and girders that support the building. It should then cruise just below these obstacles until the rubber has run down enough for the model to settle slowly back to the floor. In ideal flight, we'll have a few turns remaining on the rubber motor when it touches down. There's a wide range of indoor models, beginning with the mini stick, a diminutive class that is easy to build and can be flown in the average living room. At the top end of the scale, the F1D models are delicate, but capable of flights close to 1 hour. Imagine an hour flight propelled by a wound loop of rubber. Although scale models are usually associated with outdoor flying, they too can be flown indoors, provided the flying site is large enough. Competition is held for the easy-to-build no-cal designs, which consist of a scale-like profile fuselage, all the way to the large, more complicated models that require plenty of room to operate. This video will introduce you to many types of rubber-powered models and even show you how to build a simple model called the thermal dart. But first, let's take a look at how a rubber-powered motor works. Contrary to what some might think, the rubber-powered airplane does not run on a simple rubber band. Instead, they gain their power from 2 or more strands of carefully chosen rubber that varies in both length and width according to the airplane it will power. The standard sizes of rubber width are 1/16, 3/32, 1/8, 3/16, and 1/4 inch. Experienced flyers, especially those who fly the indoor events, will strip their rubber to even more precise widths in order to add additional seconds to the duration of their flights. For the beginner, the standard widths are totally sufficient. This simple test stand will demonstrate how the motor works. It's made up of a propeller, a prop shaft to connect the propeller to the rubber, a nose plug to provide a bearing that will cut down on the friction between the prop and the nose block, 4 strands of rubber, and a means of anchoring the rubber at the tail end. The rest of the test stand is used only for holding the other components, and of course would not be included in an actual airplane. Before winding the motor, it should be lubricated to protect it as it rubs against itself. This will increase the life of the motor and enable you to pack in more turns. Several types of rubber lube are used, including the age-old glycerin and green soap mixture. But most of today's modelers use some sort of silicone lubricant. Son of a Gun or Armor All can be purchased at your local discount store and work about as well as any. When using these silicone-based formulas such as Armor All, make sure that all of your knots have been securely tied beforehand, as these slippery lubricants can cause a knot to slip in a hurry. When tying the knot, most modelers use a simple square knot. To tie a square knot, just remember to repeat left over right, right over left. That will give you a square knot instead of a granny knot, which will slip easily. To pull the knot tight, moisten it with saliva and pull it as tight as you can. Then moisten it again and repeat the procedure. Some flyers further enhance the integrity of their knots by tying additional knots at the end of the rubber, or even adding a small drop of CA glue to the rubber. To properly wind a rubber motor, you will need appropriately enough a winder. Several are available at reasonable prices. The lightweight plastic winders come in 6:1 and 16:1 winding ratios. That means that the rubber motor is wound either 6 or 16 turns for each turn of the winder's handle. These winders are meant for smaller models with no more than 2 strands of 1/8 inch rubber. Using them on motors that contain thicker rubber or more strands can be dangerous. Some modelers use a converted hand drill, which, despite its lower ratio, can work quite well. Just count the turns the hook makes for each turn of the handle, so you will know how many turns you're packing into your motor. A word of caution: hand drills are made to be pushed on and not pulled. The pressure exerted by a tightly wound rubber motor could cause the drill to fail, resulting in a broken model or even personal injury. As a safety measure, never use the drill's chuck to hold the winding hook. Remove the chuck and permanently attach the hook directly to the drill. The handle should also be pinned securely to keep it from separating from the drill itself. There's a lot of tension in a stretched and wound rubber motor, and safety should always be your first consideration. The scale winder from Highline is perfect for the intermediate size of models such as scale models and embryo. It's sturdily built and has a 10:1 winding ratio. For larger models such as Wakefield, most modelers prefer very strong winders. This winder, sold by FAI Model Supply, has a D handle to provide a secure grip while stretching and winding. It also features an optional counter to help you keep track of the total number of turns. If you attempt to keep track of the number of turns without a counter, someone's just about guaranteed to divert your attention and cause you to lose count. Let's wind our demonstration motor to see just how a rubber motor works. We begin by inserting the winder into the winding hook. The winding hook is a simple device that makes it easier to transfer the wound motor from the winder to the prop shaft. It's generally used only on larger models. We begin by stretching our motor up to 3 or even 5 times its normal length. The theory behind this is that by stretching the rubber motor, you reduce its diameter and can therefore pack in more turns without breaking the motor. You'll learn as you advance in the hobby that the smaller the cross-section of any given rubber motor, the more turns it will take before reaching the breaking point. There are different theories about how to best wind a rubber motor. One method is to wind the motor for about half the total turns or until you feel it begin to lose its elasticity. Then begin to move toward the model as you wind. Each time the motor feels tight, it's time to move in. Keep in mind that each motor has a maximum number of turns that it will take before braking. This depends on several variables such as the thickness of the rubber, the length of the motor, the number of strands in the motor, and the age and type of rubber you're using. Even different batches of the same type of rubber will react differently. And you thought gum band models were easy. Once the motor's been wound, slip a stiff wire into the winding hook to make it easier to hold the motor while removing the winder. There's a lot of torsion in a fully wound motor of this size, and combined with the lube you are sure to have on your hands, it can be difficult to hold. With smaller motors, this will not be necessary, as you can hold the smaller motors with your fingers. Connect the prop shaft to the motor, insert the nose block, and let her rip. We've wound about 1,000 turns into our demonstration motor. Notice how the motor unwinds from the front to the back, and how the knots move aft as the motor unwinds. There's also considerable slack in the motor. This can upset the balance of the model and make it tail heavy. Braiding the motor will help to eliminate this problem. Braiding the rubber is easy. For a 4-strand motor, simply make a loop twice as long as your finished motor. Place one end of the loop over a hook and the other end on the hook of your winder. Stretch the rubber and crank in about 4 turns per inch of loop. Remove the rubber from the winder and place that end over the hook. Hook the winder into the midpoint of the new loop. Now turn the winder back and forth a couple of times and you have a nicely braided 4-strand rubber motor. For a single loop motor, you'll need to tie an easily removed knot to form a loop at each end of the rubber. Place one of these loops over a hook and the other one on your winder hook. Stretch the rubber and crank in a few winds. Now remove the loop from the winder and place it on the hook with the first loop. Hook the winder into the center just as you did with the 4-strand motor. Stretch the rubber and allow the strands to twist together. Remove the ends from the hook and tie them together using the knot of your choice. Place one end of the loop over the hook, stretch and wind back and forth a couple of times to form a braid. This is also a good time to work in some lubricant. Now let's harness that power to make a model airplane fly. We've chosen the thermal dart from SIG Manufacturing as our demonstration model because of its simplicity and ease of building. You could easily build one in a Saturday or a couple of evenings, and when built right, they fly great. To begin, you'll need a few simple tools and a building board. The building board must be flat and straight, yet soft enough to allow you to stick pins into it to hold the components in place while the glue dries. Sealing towel makes a good building board, and you can sometimes get damaged ones at your lumberyard for next to nothing. A 1-foot by 2-foot section will provide ample space to build this model if you build the wing on a diagonal. A larger board is even better and can be used for larger models later on. You'll need glue, and the cream-colored aliphatic resin glue is an excellent choice for all-around building. It's strong, odorless, and will not instantly bond your finger to your nose. Your local hobby shop will most likely carry SIG Bond. Tight Bond and Elmer's Carpenter's Glue can be purchased at most any hardware store. Do not buy white glue. Get the cream-colored glue. It will state somewhere on the container that it is an aliphatic resin adhesive. The white glues are just not strong enough to bond balsa wood. All of the parts for this model can be cut to size with an ordinary single-edge razor blade. Industrial varieties are available at hardware stores, while drugstores and discount stores sell the shaving versions. Either will work just fine, and the hardware variety are less expensive. These are extremely sharp and you must use them with care. Young people should be supervised by an adult. To hold the components in place, you'll need a package of dressmaker straight pins. Masking tape or thumbtacks are useful for holding plans and waxed paper flat on your building board. Sandpaper is often the difference between a good model and one that's just okay. With the thermal dart, the plans become the covering material and the various components are glued directly to the plans. To keep the glue from seeping through to the building board and sticking everything to it, stretch a sheet of waxed paper or plastic wrap over the board before you begin. Masking tape can be used to hold it in place. Before you begin cutting and gluing, take a moment to read and understand the instructions before you make a mistake. That might be a novel concept to most of us, but it actually works. Since the plans also serve as the model's covering, make sure that it's stretched flat and reasonably tight on the building board. A couple of thumbtacks will hold it in place, or you can use masking tape. Lay the leading and trailing edge of each wing on the plan. Then sight straight down over your razor blade and cut it to the proper angle. In order to keep from cutting through your covering, you might want to just mark it with the razor blade and then finish the cut with the part off the covering. Be careful to get the angle just right so that you have sufficient gluing surface. The leading and trailing edges are then glued to the plans. Smear a light coat of glue to the side that will contact the plans. You don't want to use too much glue as it will only add weight and will make it more difficult to cut the wing loose from the plan later. Carefully align the piece with the outline on the plan and press it in place. You may need to pin it in place to hold it flat. With the leading and trailing edges glued in place, cut the ribs to the proper length and angle. It's very important to make these cuts with the razor blade held vertically and to cut the rib to the exact angle. Failure to do this will make for a poorly fitting joint that will result in a weak and possibly warped wing. It's sometimes best to cut the ribs a little oversized and trim them to fit with a sanding stick or block. A special note as to the advantages of pre-gluing is in order. The end grain of balsa is extremely porous and will absorb most of the glue you apply. Therefore, it's always a good practice to pre-glue the end grain. Just coat the end grain with a small dab of glue and then wipe off the excess. Let it dry or at least become tacky before you proceed with gluing the ribs in place. This step will make a much stronger joint. Each rib can now be glued to the plans and to the leading and trailing edges. You still need to apply glue to the ends of the ribs even though you have already coated them with glue. Make sure the ribs contact the leading and trailing edges. Don't try to fill in any gaps with glue. It just won't work. Remember, don't use too much glue. You should also wipe off any excess. Proceed in the same manner until all of the ribs have been glued into place. Carefully mark the wing fillet length on the 1/16 inch sheet provided, using the wing as a guide. Since your first cut will be across the grain, it'll take several passes of the razor blade to cut all of the way through. Don't try to make the cut in just one pass. With the fillet cut to length, mark the tapered side, again using the actual wing as a guide. This cut will be easier since you'll be cutting along the grain instead of across it. Check the fillet for fit and use one of the sanding blocks to trim it if it's a bit too large. Once you're satisfied with the fit, glue the fillet to the plan and to the leading and trailing edges. The second wing is built just like the first. Make sure, however, that you don't glue the two wing halves together at this time. The stabilizer is built in much the same manner as the wing, so it should present you with no real problems. Just be careful to make all of your joints accurate and do not use too much glue. To build the rudder, cut the plans along the dotted line shown on the fuselage just forward of the fin. It's best to remove the tissue from this area to prevent it from becoming glued to your fuselage. Glue the fuselage to the plans. Make sure that you do not attach the fuselage upside down, as the angle at the bottom of the tail section provides the correct incidence in the stabilizer. The rudder is then built around the fuselage so that it becomes part of it. Use the same procedures that you learned while building the wing and stabilizer. Let all of these assemblies dry for at least an hour so that the glue will be dry enough for you to cut them loose from the plan. Leaving them dry overnight would be even better. With the single edge razor blade, carefully cut around the wing's outline. Cut close, but be careful not to cut into the wood. There's no need to push hard on the razor blade, as you are only cutting paper, and there's no reason to cut up your building board. If you always cut from the middle in the direction of the tips, you will have less chance of cutting into the leading edge if the blade slips. Note that the covering between the left and right wing is not cut. It's left intact to add strength to the wings when the dihedral is added. Cut the stabilizer free in the same manner and set both the wing and stabilizer aside. The rudder is cut free in the same manner. The wing saddle's made up of two pieces of 1/16 by 1/2 inch balsa and a piece of 1/8 inch square. Begin by making a mark 1/16 inch from the edge of each of the 1/16 by 1/2 inch sheets. Drawing a connecting line between the marks will help you in the next step. The 1/8 inch square is now glued to the first sheet, with its top side lined up with the line. The second 1/16 by 1/2 inch sheet is glued in place to complete the wing saddle. Try to be as accurate as you can when lining up these components, as the wing saddle will dictate the wing's position. A couple of spring-type clothespins will hold the assembly together while the glue dries. The notch formed at the top of the saddle will allow room for the V of the wing's dihedral. While the thermal dart will fly just fine without any changes, we've modified the nose section to improve performance. First, we decided to provide more clearance between the rubber motor and the fuselage. This allows more winds to be put into the motor without the notch rubbing the fuselage. Flight times went up considerably after this modification. The prop shaft that was supplied with the thermal dart was not long enough to take advantage of our modified nose, so we replaced it with a longer one. Tech Polymer sells these diamond-shaped varieties, and they can be purchased from your hobby shop or through the mail. The fuselage is 3/8 inch high. We removed a piece of balsa that was 3/16 inch high and 7/16 inch back from the nose of the fuselage. The 7/16 inch figure represents the depth of the prop hanger. Carefully glue this piece to the bottom of the fuselage, and there will be plenty of clearance between the rubber motor and the fuselage. There is, however, a trade-off, as there so often is when performance is improved. The fuselage is now weaker at this point. One solution might be to allow some very thin CA glue to be absorbed by the wood at this point. To attach the wing to the wing saddle, place the saddle over the fuselage, but don't glue it in place. Fasten the fuselage to the building board using a square or triangle to make certain that it is at a 90-degree angle to the board. Both wings are now glued together and to the saddle with the tips raised 3.5 inches above the board. Although this is not a super critical measurement with this model, both tips must be raised an equal amount. We used a couple of bottles to support the dihedral angle while it was drying. You should be able to find something similar around your workshop. Allow this assembly to dry thoroughly before moving it. Leaving it overnight is highly recommended. The stabilizer is attached to the fuselage with the tissue side down. Check it carefully to make sure that the rudder is perpendicular to the stabilizer. The same bottles used to support the wing dihedral were again used to hold the rudder upright at a 90-degree angle. The front of the fuselage needs to be raised to allow for the angle on the bottom. Music wire was used for the rear anchor hook, and it was wrapped with thread and coated with glue for added strength. The wing saddle is slipped over the fuselage and held in place with the small rubber bands. Do not glue the wing saddle to the fuselage. It must be movable to provide flight adjustment. Then attach the propeller and nose piece. You are now ready for the rubber motor, and for best performance, you should substitute a longer motor for the one supplied with the kit. It will greatly improve your model's performance. This done, we're ready for our maiden flight. Select a calm day and an area with plenty of room. Thermal darts are capable of excellent flight times and need room to maneuver. Have someone hold the model for you by placing one hand behind the wing and the other at the nose. Your helper must hold the propeller to keep it from turning. It might be a good idea to explain to your helper that these models are delicate and that balsa breaks easily. Move forward as you wind, and when you have reached the model, grasp the rubber securely about a ½ inch from the winder. Let the winder unwind a few turns so you'll have a loop. Then carefully slip the motor off the winder and transfer it to the rear hook of the model. Winding hooks are not used on small models like the thermal dart, so use caution here as the lubricated motor will be slippery and difficult to hold. With the motor secured, take the model from your helper, using care to keep the propeller from spinning. Hold the thermal dart with one hand on the fuselage at about the balance point and the other hand keeping the prop from turning. Release the prop and a split second later shove the plane forward in a level attitude. Don't throw the model and don't point its nose up. Just gently shove it forward with the nose level. The model will fly right out of your hand. As the model flies, observe it carefully for any radical flight characteristics. Our model had a severe stall on its first flight. This is an indication of a tail-heavy condition which we corrected by moving the wing back. The next flight was much smoother. If the model had dived on the first flight, we would have moved the wing forward. Just remember to move the wing toward the nose if the model dives, and toward the tail if it stalls. When you begin to build more sophisticated models with fixed wings, the solution won't be this easy. Once you're satisfied with the flight of your model, begin to add more and more turns to the rubber motor for longer flights. Just remember that rubber that's wound too tightly can break. Your thermal dart should give you many wonderful flights and teach you a lot about rubber-powered model airplanes. The SIG Cub is a logical step up from the thermal dart as its wing has an airfoil and it uses a more standard method of covering the flying surfaces. At the same time, it's not difficult to build. By following the directions closely and using what you learned while building the thermal dart, you should have no trouble in building a model of your own. We've modified our Cub somewhat in order to demonstrate some of the procedures used to adjust a model for flight. Experienced modelers refer to adjusting as trimming a model. The Cub already has an adjustable rudder, but we've added trim tabs on the stabilizer and the wing to demonstrate the effect these have on flight. But before we begin flying our model, let's take a look at balance. Each model design has a definite CG or center of gravity around which it should balance for optimum flight. This is usually shown on the plan. If it hangs nose down when suspended at this point, it will most likely dive. If it hangs tail down, chances are it will climb until it stalls. Carefully balancing the model before test flying will help to limit this problem. When you begin building models with stationary wings, you won't be able to correct this problem by moving the wing. Weight will have to be added to the nose or tail. Just remember that any weight added to your model will reduce the flight duration. Misaligned or warped flying surfaces are a more serious problem. They can cause the model to turn in some mysterious ways. The only solution is to correct the problem or add trim tabs to counteract it. Correcting warps is never easy, but sometimes the offending surface can be held in steam and then twisted in the opposite direction of the warp. Hold it in this position for a few minutes and it should return to a warp-free surface when released. To demonstrate the problems caused by warps, we'll use the trim tabs on our SIG Cub to simulate warps. Let's pretend that the left trailing edge of the wing is warped up. This can be a particularly dangerous situation as it'll work in conjunction with the torque of the motor to roll the plane to the left. If the right wing trailing edge is warped down, it will have the same effect. If either of the wing trim tabs are moved in the other direction, they will tend to roll the model to the right. This is actually useful at times to counteract torque. The rudder is used to turn the model. You'll quickly learn, however, that too much rudder can cause your model to spiral dive into the ground. This is particularly likely during the power portion of your flight, since the rudder is more effective at higher speeds. The stabilizer tab, or elevator, causes the model to climb or dive. Bending it up will cause a climb. Too much up in the tab will cause a stall, such as illustrated here. Conversely, bending the elevator down will cause a dive. Very little elevator change is needed to cause a rather sharp climb or dive. Since the forces acting on a model airplane are much different during the powered and glide portions of flight, most rubber-powered models use thrust offset as an additional means of control. To illustrate how thrust offset adjustments work, let's take another look at that nice little rear-wing speedster that had a tendency to spiral into the right. Experience has taught John to always carry a variety of balsa shims with him when trimming a new model. By having shims in a wide range of thicknesses, he can make temporary thrust adjustments in very small increments. It's a good idea not to wind the rubber motor too tightly when making test flights. Shorter flights mean less chance of getting into trouble. The shim is inserted between the nose block and the fuselage. The problem you're trying to correct determines which side it will go on, or whether it will go on the top or bottom. The shim is just a temporary measure and will be replaced by a permanent and better looking fixture once the problem has been corrected. With the shim in place, the spiral has not only been corrected, but the model now circles left under power. John will continue to try different shims until he achieves just the flight pattern that he wants. Most models use a combination of right and down thrust to handle the forces of powered flight. Some are even designed to fly one direction under power and then glide in the opposite direction. These same principles of flying surface and thrust adjustments work with all rubber-powered models, although some flyers have refined them considerably. This is especially true when it comes to contest flying, as it's here that you'll meet the very best from your area, the nation, and maybe even the world. The competition can be fierce, but don't let it intimidate you. You'll learn something at every contest you enter, and eventually, you'll be the expert. There are even some very enjoyable events designed for beginners, so you can compete in them before moving up to the more complicated models. Embryo is an interesting event to consider, and the construction and flying of a well-designed embryo model is well within the capabilities of a novice modeler. The embryo model is judged by its ability to take off from a card table and stay aloft longer than the competition. There are kits on the market such as the Prairie Bird by Peck and the Hornet by Micro X. Plans are also available from sources such as Flying Models and Model Aviation. No-cal scale is another event designed for the novice. These are profile models, but must retain the outline of the airplane they represent. The maximum wingspan allowed is 16 inches, and contests are held both indoors and outdoors for these fun models. Rubber-powered scale models are miniature reproductions of full-sized aircraft. They can be as simple as a Piper Cub or as complicated as a multi-engine bomber. Multi-engine rubber power is not for the novice, so select a good high-wing model for your first efforts. There are many good kits on the market and an almost unlimited number of plans available. Scale models are judged for their likeness to the real airplane before they're flown. The builder must submit documentation to prove that the subject he's chosen really does exist. In Flying Aces scale events, bonus points are awarded for such items as floats, multiple engines, and aircraft with more than one set of wings. Scale and bonus points are then added to the flight score to determine the winner. Old-time rubber events give the modeler a chance to recapture the early days of model airplane flying. It's an especially interesting event, and the times posted by these decades-old designs are amazing. The P-30 event is a good initial step toward the more sophisticated endurance events that require more complex propeller assemblies. This Mini-Maxer is a bit small for P-30, but if built light enough can turn in some very acceptable flight times. You'll find the rules for the various events in the AMA and Flying Aces Club rule books. Regardless of the event you choose, or even if you just fly for fun, you'll quickly learn that achieving the best possible flight is often a compromise. And one of the biggest compromises you're sure to encounter is the propeller. To get the best climb out of any model, large propellers with ample blade area often give the best results. The downside of this is that once the rubber motor has run down, the propeller becomes drag, and drag will reduce the model's ability to glide. There are two methods commonly used to reduce propeller drag: the folding prop and the freewheeling prop. The folding prop shown here is the more efficient, but also more difficult to construct. Once the propeller stops turning, the slipstream pushes the propeller blades back along the fuselage, thereby cutting the drag to almost nothing. The result is a rubber-powered model with about the same drag as a glider. Because of their complexity, folding props are mostly used in the more competitive duration events. In fact, they're not even allowed in most beginner and scale events. The freewheeling propeller is an alternate to the folding prop and is allowed in beginners and scale events. This propeller does not fold, but instead freewheels in the slipstream after the rubber motor runs down, thus reducing drag. Some freewheeling props are very simple, like this one used by the thermal dart. The freewheeling device is molded into the propeller hub, and the propeller shaft is bent at a 90-degree angle to engage it. This more complex version of freewheeling prop requires more skill to construct. You'll need to do some wire bending, metal drilling, and soldering. Notice how the propeller disengages from the shaft so that it can freewheel. This easily constructed freewheeling device needs only a piece of aluminum tubing and a short piece of wire. The prop shaft pushes on one end of the wire during the power run. Then, when the prop begins to freewheel, the wire drops out of the way to allow it to spin freely. While plastic propellers win a lot of contests, some experienced builders often go beyond the plastic propellers and carve or build their own. There are also propeller blanks on the market that have most of the carving done. With them, a little cutting and sanding can produce a nice, efficient propeller. For lightweight models, propeller blades can be cut from sheet balsa or 1/64 inch plywood. They're soaked in water to make them pliable. The blades are then strapped at a 15-degree angle to a form, such as a can or a bottle, of about 3 inches in diameter. The blades can then be dried in an oven or microwave at low heat. Or, if you're in no hurry, the blades can be left to dry overnight without any heat being applied. Remember that you cannot put metal in a microwave. Once dry, the blades retain their shape. Bamboo skewers that can be purchased in the cooking department of many stores make excellent propeller hubs. Cut the skewer to the proper length and drill a hole the diameter of your prop shaft in the center. Glue the blades to the hub using a pitch gauge. Plans for this homemade version were published in the Flying Aces newsletter. Commercial versions are also available. The hub is rotated 180 degrees and the second blade glued on just like the first. Very workable blades can be fashioned from foam beverage cups. Just visit your favorite fast food restaurant or coffee shop to see what size of a drink you will have to consume to get the proper blade size. Prop shafts are usually made of either 1/32 or 3/64 inch wire. They're available ready-made, or you can bend your own. Using an S-bend will help keep the rubber motor from creeping forward on the shaft. To make an S-bend, grip the loop of the shaft firmly in a vise or with locking pliers. With a second set of pliers, twist an S-bend into the loop that will hold the rubber. The result will be something like this. For safety and convenience, you should use a stooge to hold your model while you wind. Homemade versions work just as well as the commercial variety. And rubber power flyers have gotten pretty creative over the years with the stooges they've developed. If you decide to make your own, just be sure that you build it sturdy enough to hold the type of models you'll be flying. Obviously, peanut scale and indoor models won't need as strong of a stooge as the heavier P30 and old-time classes that use more rubber for power. After your stooge has been anchored, fasten the model by inserting a wire through both the stooge and the rear rubber anchor. The rear anchor should be made from aluminum tubing of a size suited to the model. Next, use a long wire hook to run the rubber motor through the blast tube and attach it to your winder. Using a blast tube will protect your fuselage in case a motor breaks while it's being wound. Some flyers attach the rubber directly to the winder, while others prefer to leave the long hook between the rubber and the winder as they crank in the turns. Stretch the motor out 3 to 5 times its length and begin to wind. The total number of turns you pack in will depend on the length and thickness of the motor, the number of strands, and the type of flying you're doing. A serious competitor will crank in as many turns as he dares, while the sport flyer may tend to be more conservative. Some flyers use a torque meter instead of counting turns. No matter how many turns you decide on, wind about 50% of them in with the rubber fully stretched. Then begin walking slowly toward the model as you wind. The wire will allow you to pull the blast tube from the fuselage and transfer the rubber to the prop shaft. With the motor attached to the prop shaft, the nose block is inserted into the fuselage. Be careful not to put it in upside down or all of the thrust adjustments will be reversed. Many modelers build some kind of key into their nose blocks to prevent it being inserted inverted. You should at least mark the block so that you can see which way it should go. Carefully remove the model from the stooge and you're ready to fly. What could be more beautiful than a rubber-powered model flying gracefully overhead with its propeller producing a soft whirring sound? It's easy to see that there's a lot to learn about building and flying rubber-powered model airplanes, but learning is half the fun. To further your knowledge, read one of the many books that have been written on the subject. Don Ross's book is an excellent example, as is Bill McComb's Making Scale Model Airplanes Fly, and Bill Hannon's Peanut Power. Indoor Models by Lou Gitlow explains indoor flying in logical steps. Fred Hall has written a useful book on indoor scale models. Model Aviation, the official magazine of the Academy of Model Aeronautics, and Flying Models both carry information of interest to rubber power modelers. By joining a local club or one of the national special interest groups such as the National Freeflight Society or the Flying Aces, you'll have even more information available. Model aviation is a hobby that has no age limits. It can be enjoyed by youngsters and senior citizens alike. The secret is to never stop learning and to have fun.